Good morning, everyone. Yesterday we had discussed few of the logic gates. Briefly, we'll once again revise. AND gate, if you just recollect, this is the equivalent switch diagram. Actually, the gate representation is this. The digital gate representation is this. And this is the US symbol, which we are not concerned much about US symbol. We should know this symbol. If required, if for you this switching diagram is for your understanding. Okay, this is the AND gate symbol. Inputs A and B in a block, square block. You have AND ampersand, and output is A dot B, that is equal to Q. Q is the output. So this is the symbolic representation, and as the uh, logic of operation is concerned, it is shown in the truth table. And the equation is A dot B is equal to Q. Okay, AND gate. Now let us first understand. For output Q to be available, both A and B should be switched on. Both A and B should be switched on. Now this switch on word is as far as this switch circuitry is concerned, but in digital circuitry, both A and B should be either on or off. If you want to have Q to be on, both A should be on and A and B should be on. Or if you want Q to be high, A should be high and B should be high. If you want Q to be enabled, then A should be enabled and B should be enabled. So the terminologies differ. Basically, we'll see the truth table, the things will be clear to you. Okay, these are the inputs A and B, and this is the output Q. Okay, in AND gate, if A is off or A is 0 and B is also 0, B is also off or 0, then output will be 0. Okay, now if A is off or 0 and B is on in AND gate, both should be on to get on signal. Now A is 0 and B is 1. The output is 0 because A and B are not 1. Okay, so it is 0. Now A is 1, that is on, B is off or 0. Still it is 0. Now A is 1, that is A is on and B is also on. A is on and B is also on. Then only there will be output Q 1. So A is enabled, B is enabled, and B is enabled, then Q will be enabled. A is true, B is true, then Q will be true. So the words will change. Basically, it will be in the form of ones and zeros. If A is 1 and B is 1, then I'll have output Q as 1. Now these are the logic. You have the requirement of some alarm. In that case, I want the alarm to be on when condition A, that is the door is interrupted, the door at the entrance is interrupted, so that interruption at the outside gate is 1, that is on, and if your house gate, there also have one sensor, that is also interrupted, then 1, 1, if that is the case, then the buzzer or the alarm should be put on. So these are the situations wherein we can make use of such logic. So this is the AND gate. Then we have, yesterday only we had seen, this is the OR gate. We should bother about the first symbol. This is for understanding, the switching circuit is for understanding. And this is our ISO accepted representation of OR gate. Forget about this US symbol. We are not much bothered about this US symbol. Switching diagram, if you want, for understanding. And then this is my logic diagram for OR gate. Now, what is the equation for OR gate? For AND gate, it was A dot B is equal to Q. Now for OR gate, it is A plus B is equal to Q. Now see, through switching diagram, we can understand it. OR gate, either A or B, if those are on, I can get two output as on, right? So condition A or condition B, if these are fulfilled, I'll get output Q. This is what this OR gate says. So the symbol is, as in the case of AND gate, it was ampersand. Here for OR gate, it is greater than or equal to 1. These are inputs A and B, and this is the output Q, which is equal to A plus B. Well, let us see the truth table. And as I said, we are writing truth table in terms of bits, zeros and ones. Or the conditions could be 1 for enable, 0 for disabled, 1 for true, 0 for false. Okay, 1 for on, 0 for off. The conditions differ, but the digital representation is in the form of 1 and 0. Now, A is 0 and B is also 0. Then the output Q will be 0. If A is 0 and B is 1, so A is 0 or B is 1. So one of the two inputs is 1. So output is 1. A is 1, that is A is on and B is off. Still there will be output Q as 1. If A is 1, that is A is on and B is on. Still the output will be 1. So these are the truth figures of output which will decide which gate I can use for my particular application. These two we had seen yesterday. Just quickly recap that and then we'll go to NOT gate. NOT gate. The circuit is not shown, but the symbol, either US symbol, you can use input A, and this is A dash or A bar. That means inversion of input is done by NOT gate. So there is a small circle and a line. So this is our standardized representation. Input A, 1, circle and line, and A bar. This is my output. So this A bar corresponds to inversion. So what the NOT gate does, whatever is the input, what is the state of the input, that will be inverted and given as output. So the equation is output Q is equal to A inversion or A inverse or A dash or A bar. That is my output. So the truth table is, if A is 0, if input is 0, what the NOT gate will do? It will invert whatever is the input. If A is 0, it will make it 1. A is 0, it will make it inversion 1. If A is 1, it will invert it. It will make it 0. So this is the NOT gate. So it will also have certain applications in our logical circuitry. So this is NOT gate. Remember the symbol. Input A and output Q is A dash or A bar. That is small circle with a dash. Next is NAND gate. NAND gate. So that is AND plus NOT. AND plus NOT. So what was NOT gate doing? It was just doing inversion. And what NAND gate will do? Whatever is the output I'll be obtaining through AND, NOT gate will simply invert it. Getting it or not? Whatever output I'll be getting through AND gate, NOT gate will invert that output. So this is a symbolic representation. Input A and input B, AND gate symbol and ampersand. I'll be getting A dot B, and then I have NOT gate symbol. Okay, small circle and dash. The output Q is equal to A dot B dash. A dot B dot A dot B dash. That is the inversion of A dot B is equal to Q. Well, let us see. Please be a bit attentive. A is 0. AND gate. For getting some valid output, I need A and B. AND gate. A is 0. B is also 0. The output will be 0. isn't it? For AND gate, the output will be A and B. Output will be 0. But what the NOT gate will do? That 0 will be inverted into 1. So 0, 0. Output of AND gate will be 0, and the NOT gate will invert it to 1. Okay. For AND gate, A is 0, B is 1. For AND gate, both should be same to get that same output, isn't it? So A is 0, B is 1. What will be the output for AND gate? 0, isn't it? 0. So what the NOT gate will do? It will invert that 0 into 1. Now the third condition. A is 1 and B is 0. In AND gate, A is 1 and B is 0. So the output is of AND gate is 0. And what the NOT gate will do? That 0 will be inverted to 1. Getting it or not? Now, final state. A is 1, B is 1. So A and B are 1. For AND gate, the output will be 1. For AND gate, the output will be 1. And what the NOT gate will do? It will invert that output. So I'm getting A and B as 1 and 1. So output is 1. And the NOT gate will invert it to 0. This is the truth table for NAND gate, friends. Let us see NOR gate. So the symbol is NOR is OR plus NOT. NOR is OR plus NOT. So input A, input B. For OR gate, the symbol is greater than or equal to 1. This is A plus B is the symbol for OR gate. And NOT gate, 1 small circle and dash. Okay. So what is the equation? Our output Q is equal to A plus B bar, or inversion of A plus B. Let us see the truth table. A is 0 or B is 0. Output will be 0. And what the NOT gate will do? It will invert that 0 into 1. If A is 0 and B is 1, so A or B, either of the two is 1. So the output will be 1. What the NOT gate will do? That 1 will be converted into 0. So the output Q will be 0. Now, A is 1 and B is 0. So A or B, either of the two is 1. So the output will be 1 for OR gate. And what the NOT gate will do? It will invert that 1 into 0. Okay, finally, A is 1 and B is 1. So A or B are 1. So the output would be 1. And what the NOT gate will do? It will invert that 1 into 0. So this is my NOR gate. NOR gate. Okay, so this is the truth table for NOR gate. Let us see. XOR, or exclusive OR gate. Exclusive OR gate. Or it's a combination for AND plus NOT gate for one input. AND plus NOT for one input. Let us see the symbol. So A, input A, and B is, this is a NOT symbol, not for one input. And these are getting you to my OR gate, isn't it? And the output will be A plus B inverse. Output is A plus B inverse is equal to Q. A plus B inverse is equal to Q. So let us see the truth table. See here. If both inputs 0 or 1, the output is 0. This you remember, you must remember. If both the inputs are 0, if both the inputs are 0, if both the inputs are 0, output is 0. If both the inputs are 1, if both the inputs are 0 or 1, both the inputs are 0, output is 0. If both the inputs are 1, the output is 0. Remember this is very important. If both the inputs are either 0, output is 0. If both the inputs are either 1, output is 0. So for 0, 0, output is 0. For 1, 1, output is 0. If one of the inputs is 1, then the output is 1. Very important. If one of the inputs is 1, output is, if one of the inputs is 1, output is 1. So 0. This is one of the inputs is 1. Output is 1. One of the inputs is 1. So the output is 1. Okay. So this is the truth table for exclusive OR. Why we are calling it as exclusive OR, friends? So I am getting equation as A plus B inverted is equal to Q. So this is the exclusive function of the OR gate that I am obtaining, and that's why in certain situations in mechatronic devices I want this XOR gate. I think, friends, we will stop for today.